Okay, so when we're talking about that limiting reactant, okay, we know what things about this?
It's what's left. I mean, it's what doesn't have enough of something. Limiting reactants make less of a material than the other one.
Good, so it stops making products.
She said that was stupid. Yeah.
I knew that was what you were trying to say. You're good. Okay, so it stops making products. So it's going to be the one that when you calculate how much product each one's making, it's going to have the lowest number of products formed. So what did we find out yesterday? How many calculations do you always have to do? 2. Okay, so you're always going to do 2 calcs. Most of them are going to be a gram to mole, or you can go all the way and go gram to gram for both of them and decide who's the smallest. If you're going to take this approach, just make sure you finish the question, which is figure out what it is in grams. So take that mole answer and convert it to grams. Okay? All right, so you guys go ahead and try and give number 3 a try. You guys got your group members, and then we'll go over it in about 2 or 3 minutes. All right, so when you have this, we know that we had to do 2 calculations. So I'm going to do the one where I'm just going to stop at moles, and then I'll continue on once I get that answer, okay? So to start us out, we had 250 grams of copper. You brought words down to the right, turned it into moles, okay? That's 55. All right. And then we took words down to the right again. And who did I relate it to? Silver. Good. So moles of silver on top. This is copper. All right. And then where do I get this information from again? The coefficients. Good. So you had 1 mole of copper and 2 moles of silver. Okay. So when you guys typed that in, what did y'all get?
7.887. Is that a 6355? Okay.
7.87-ish? Okay. All right, then I took the other one and I ran through the same calculation, except now I'm going to be talking about that silver nitrate. Do it different. Okay? And once again, I related it to the silver. So our mole ratio between these two is a 2 to 2. So really, that part doesn't even matter because they cancel each other out. So you have 340 divided by 169. That's about how much? 2. Good. It's 2.00. Sorry, my bad. All right, so we have 2. So who is my limiting reactant? So who is my limiting reactant? Silver nitrate. So your answer in the first little blank is silver nitrate. Who's your excess reactant? Copper. Now we want to know the mass. So what we're going to do is we're going to take that 2 moles, and I'm going to start there, okay, of silver. And I'm going to say 1 mole of silver is 107.87 grams. Okay. What did you guys get? 250.74. Cool. So to keep it to 3 sig figs, we're going to round up to 216. Okay? Okay. So now we have to approach the second part of the question. The second part of the question is asking us how many grams of the excess reactant are left over. So who am I talking about in this problem?
Copper.
Copper. We want to know information about this guy. What did we start with copper? 250. So we're going to be taking that 250 and we're going to subtract something to figure out what's left over. Okay, that's our goal. But we have to have that something right here. So what you're doing is you're relating your limiting reactant now to how much copper was used when that limiting reactant was used up. Okay? All right, so I'm going to zoom out, give myself a little more room. So what we're going to start with is you have to start with the 340 grams of your silver nitrate. And my people who already notice, do you have to start there? Could you start technically right here?
Yeah.
Right. It's 2, right? So we already know that information. But I'm gonna do the long way. It's okay. 1 mole. And now I'm gonna have my mole bridge between silver nitrate and copper. So there's 2 moles of silver nitrate for every 1 mole of copper. And then take it one last step. 1 mole of copper is 63.55. Okay, before even typing into your calculator, I want everyone to look at this for a second, because you could do this one in your head. Okay? What did we find out before that all of this was? 2, right? So what's 2 divided by 2? 1. So we're doing 1 times 63.55. What's my answer? Yeah, there we go. All right. So if you wanted to, you could have typed it in. That's fine, but that's your answer for that, okay? So where does this number go? Now that I found out how much copper was used, so this is copper used. Now I'm going to subtract it from that 250. So I have 250 minus 63.55. And you should get 186.45. All right, so we're going to move on from this. This is being recorded so you guys can look at it online if you didn't get it all. Move on to the page that you have in front of you, the one that you picked up. Or I'm sorry, or I passed out. I don't know, whatever. All right, so let's focus in on this page first. Okay, the one with all the words on it. All right, so this just lays out what we've been working on for the past couple days, and that's your limiting reactant. And now I'm going to bring in finally that theoretical actual yield, which a lot of you guys ended up figuring out on your own, so that's cool. So this is, we're going to just run through these steps so you get your vocab down. I'm going to have you guys underline or circle. Feel free to follow along with that, or a highlighter, doesn't matter. And then we're going to try a few on your own, okay? A few more. And now they're going to be a little bit harder than the one that we did for the warm-up, okay? All right. So this just says a limiting reagent. So I wanted to point out this word right here, the reagent. You will hear you'll hear it be called a reagent as well. We use that and reactant kind of interchangeably. All right? So don't be freaked out if we say reagent. It is not a typo. That's really what we call it, okay? All right. So it limits the amount of product formed. You guys have already told me that. Okay? Your limiting reagent gives the smallest yield of product calculated from your reagents available. The smallest yield of product is now going to be called your theoretical yield. So basically, all those answers that you've been finding, those are your theoretical yields. Okay? And that's going to come from calculations. All right. So to find your limiting reagent theoretical yield, most of this should be a review for you. So first, you're going to find the moles of each reactant, and then you're going to calculate the moles of a product. I will tell you right now, I've combined those 2 steps for you. Usually what we do is we just go straight to moles. So you guys are doing a railroad track of grams of a reactant, grams reactant, mole reactant, and you go right into your mole bridge. Right? So mole reactant, mole product. That's what I taught you. So it's the same thing, it's just steps 1 and 2 linked together. You're more welcome to break it up if it makes more sense to you. All right. Then, identify the reactant giving the smaller number of moles of product. Okay? That's your limiting reactant. Finally, calculate the grams of product produced. So So give them what they want. If I'm only asking for moles, you don't have to do that. Okay? All right. So now to these words. Okay, so theoretical yield is the one that you calculate. Okay? So it's coming from information given to you about how much product you're using. Okay? Actual yield is also called your experimental. Okay? Meaning it comes from the experiment or it's formed in the laboratory. So it's the actual results that are measured. So, will actual yield ever be more than theoretical yield?
No.
Only one person?
Maybe it would be.
Yes.
So, if I calculate, if I say that you had 5 grams of aluminum and 5 grams of hydrochloric acid or whatever, and you guys put them into a little test tube, what happens? Sorry, not aluminum. Do zinc. What do you guys know happens when you drop zinc into hydrochloric acid? What happens? Bubbles. Do you guys ever put a stopper on it? No. So where do the bubbles go?
In the air.
In the air. So we don't measure that part. We measure the liquid part, right? Okay. Am I going to have everything necessary in there if I had that open container and stuff floated out or maybe popped out and stuff like that? No. Okay. So actual yield should be less than theoretical. Okay? That's a good way to check, did I do my theoretical calculation correctly? If it ends up being less than your actual, you probably did something wrong because most of the problems we give you are clear-cut. They're not going to have mistakes. Now, in the case that you're doing a lab and your theoretical does come out less, so your actual, you come up with more product, you contaminated it. You either didn't measure right or you contaminated it. You could have sneezed into it, you could have drooled into it. No, I'm just kidding. But basically, any oils from your hands, maybe it caused a separate reaction, okay? Anything like that, that would be the only reason why actual would be greater than. And in that case, you have to start over. It should never be more than, okay? All right. Here's your little formula. I don't feel like I really have to go over that one too much. You're going to put the small number on top, big number on the bottom, multiply it by 100. This is like giving yourself a grade on your lab. Because if you get 95% yield, is that pretty good?
That's pretty good.
That's really good, right? You got an A on your lab, yay. If I get like 43%, that's less than half, right? You produce less than half of what you were expecting. That's not so good. That's not good lab procedure. So it's like giving yourself a grade. Don't forget that when multiplying by 100 means you move that decimal 2 to the right. Okay? So you could skip the whole times 100 part and just move it 2 to the right. All right, flip it over and let's look at the back. I am not planning on going through all this because I feel like it's pretty self-explanatory. They're just giving you an example. So if I have not been working well for you, please read this. Just to kind of fill in, one little question that a lot of people had was this. The times in a line is the same thing as our railroad tracks. Okay? So if the times in a line is kind of confusing you, you can always replace it with the railroad tracks. Otherwise, just leave it. Okay? I wanted to point out they are going grams to grams in their 2 examples. So they're going all the way. I usually stopped you right here. Okay? So I just wanted to point that out as well. Below is giving you an example of your actual and theoretical yield being used. So you can refer to this page too. Okay? Okay, we're going to look at this page that I just handed you. We're going to start with number 1. I'm just going to run through one example to kind of point out the things that are going to look a little more challenging, okay? So we're going to do number 1 together. There is not a lot of room on this page. That was my intention, so you could grab your own piece of paper and you could take all the room you need. So now is an okay time to grab a piece of paper. Okay, so for this problem, it says calcium hydroxide is used to neutralize acid spills. Okay, it reacts with hydrochloric acid according to the following equation. Okay, so you see that we've got two reactants, two products. Quick question, what type of reaction is this?
Double replacement.
It's a double replacement. Good. Okay, and it's a neutralization. That's what it's also called. All right. Letter A says if you have spilled 6.3 moles, because that's what we would count. It's kind of weird, but this is an easy one to start with. Okay, so 6.3 moles of hydrochloric acid, and then you put 2.8 moles of calcium hydroxide on it. Which substance is the limiting reactant? So we're going to start with that one. Okay, so we already know how many calculations do we have to do? Two. All right, so I'm going to put 6.3 mole. I'm going to start with this one. HCl times in a line. All right, where am I starting on this? Which city?
Mole City.
I'm in Mole Town, right? So where do we go? Like right away. The mole bridge, exactly. So we're going to go right into that mole ratio. But here's the problem. What do I put on top? Does it specify anything?
No.
No. All right, so this is cool. That's actually good. That means you get to just pick whichever one you want. All right? You can always do that. You can pick the water or you can pick the calcium chloride. I'm going to personally just pick the calcium chloride. If you want to do water, you can be rebellious and you do it on your own. No, it will not be different. Okay. So, hydrochloric acid, we will have 2 moles here, 1 mole here. Wait, let me clarify. Your answer will be different, but you will still get the same limiting reactant.
Oh.
Make sense? Okay. All right, cool. Got it. Okay, so looking at this, what can you do? Can you guys do this mental math? Come on, you can do it.
It's like 3.15.
3.15. There you go. All right. All right. Let's go to the other one. 2.8 moles of that calcium hydroxide-ishness. It's okay. You can still ask questions, just the excess talking is going to show up. All right. Okay. So here's the catch to that. You have to use the same one both times. So you can't just switch to water now. You have to compare apples to apples, oranges to oranges, okay? You can't do opposites. So here we have 1 mole of calcium hydroxide for 1 mole of calcium chloride. Again, do we have to type anything into our calculator? No. What's my answer? 2.8. Good. All right. So who's my limiting reactant?
Bottom one.
Calcium hydroxide.
Good. Calcium hydroxide. Okay. So that's the answer to the first one. They just wanted to know who's the limiting reactant. Then it says how many moles of the excess reactant remain. So we don't even care about how much product is being made. We just want to know how much is going to be left over, all right? So this is the other way that these problems are going to look, and that's what I wanted to point out to you. So how many moles of the excess remain? How did we do it in our warm-up? Who remembers? What's our end goal? We're going to be doing what?
Didn't we have to
We're going to subtract. Good. So we're going to subtract the original amount that we had of our excess guy. So 6.3 moles, and we're going to subtract some answer to get left over. Okay? Now we got to figure out how to get this. Who remembers what we did? What did we start with?
You start with the limiting.
Good. You start with your limiting reactant. So we're going to take the 2.8 moles of calcium, blah, 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 blah. Okay? That comes down to the right. Moles, calcium, blah, 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 blah. Who do I relate it to now? Yeah, hydrochloric acid, the HCl. Good. Okay? So this is a 1 to 2 ratio. Can you guys do that one in your head? 5.6. Good. Awesome. All right. So do this one in your head too.
Wait, 2.8
The
is the
answer.
mole of calcium.
I'll answer your question. What did you guys get? 0.7 moles. Good.
Wait, so the person didn't put enough
Okay, well, it's better for you.
Good point. I like that you brought that up. So he just brought up so that calcium hydroxide is supposed to neutralize it. But if we have this much hydrochloric acid left over, did he neutralize enough? No, he needs to put some more. So good. That's a good point. So I was just asked where the 2.8 was coming from. Remember, that's coming from what they give you. That's the starting point. The 2.8 moles is what you had of calcium hydroxide. Are there any other questions for yourself? It's pretty straightforward, okay? So you just kind of got to get yourself into the routine. Make sure you're still remembering all your stoichiometry, okay? All right, so you guys are going to go ahead and work on at least 3 or 4 others, okay? You guys have at least 10 minutes, so keep going.